As everyone knows, the internet is magic, and it uses tiny ether elves to transport information across long distances. But what if we pretended the internet were actually based on logical procedures? In order to achieve this, we'll construct a few visual representations of data units, such as pings, messages, and images, and then we'll expand the network to represent transmission of data across the internet. We'll start with a couple of computers and not worry too much about the construction of these apart from the data types we want them to be able to process. We can begin with one of the simplest data units, a ping. This is basically an "are you there" check, which helps one device know if another device is connected to the network. If we look at this simulation of sending a ping, we can notice a few important fields. We have the address of the sender and recipient, you can think of it like a home address, and we have the type of data coming in. There's some other information as well, but for our purposes, we don't need a one-to-one recreation. We will have a tag that announces that the incoming data is a ping, we'll specify if it's a request or response, and we'll give the incoming and outgoing addresses. Each of these components will have a byte of data, which means 8 numerical places and 256 possible combinations of 0 and 1 values, and this should be plenty to work with. I'll add a little visual dot for each byte, so here's what it looks like when the computers send that information to one another. I've given each computer an address, and for now, I'm just using a half byte, which is also called a nibble. So you see when I put the target address in the bar below, the computer sends a ping to that address. Now we need some way to process that incoming data. I wanted something semi-realistic where the data physically reaches the computer, like electricity or light traveling through a wire. So I made the computer detect the collision of these bytes, and then they get destroyed and stored in a memory bank. Now we just need to have the second computer send out the same data with the addresses swapped and the response byte flipped, and we have a full ping. You may notice there are 5 bytes of data being transmitted now, and that's because I also added a length field to indicate the length of the incoming data. Here the length is just 0, but it will be important for other data units such as text. For text, we have the same basic foundation, but there will also be an uncertain number of bytes coming in, where each byte represents a text character. The length byte is important here because the computer needs to know how much data it should expect, so it knows to stop listening for more data and process what it has. To make this happen, we'll first need to be able to convert between binary and plain text. It would be totally doable to make my own dictionary for what combination of zeros and ones equals what letter, because it's totally arbitrary, but I'll just use a built-in function. During the transmission of the data, you can see the binary representation of the letters that are sent. Now we just need a screen for that data output. So we convert back from binary to text, and there we go, we have messaging capability. I want to emphasize here that the second computer never directly receives the string hello. It has to reconstruct it entirely from the incoming data. Alright, having a bunch of white dots doesn't exactly give great visual clarity, so I added in some colors. This will be especially important in a couple minutes. For now, the addresses appear in the 3rd and 4th positions, and you can see with the ping that they become swapped. For text, all of the text data after the length byte is colored purple. Let's move on to images. The first challenge is that I want each byte to represent the color of 1 pixel from the transmitted image. Normally, color is expressed in at least 3 bytes, 1 for each red, green, and blue. However, I can do some compressing and fit the colors into a single byte. We'll dedicate the first 3 to red, the second 3 to green, and the last 2 to blue. The resulting color will be less accurate than the input image, but I think it will be worth it for what I have in mind. Let's add in a new data unit and give it a new identifier byte. And then we'll have a function that reads every pixel of an input image, and the amount of pixels of that image will be the number represented by the length byte. Here's a 32 by 32 pixel image, and this is what it looks like in transmission.
One eternity later.
Let's make the data bytes now represent the color of the pixels. Lastly, we need a texture to reconstruct the image on. Here's a smaller image at work. And now for the larger image. Oh, something got messed up here. Let's try that again. Nice, that's working. Now obviously the culmination of the internet is the ability to share cute animal photos with one another, so let's make sure we can do that. This photo looks good. I just need a smaller resolution version so that it doesn't take an eternity to transmit. Let's see how it looks. Beautiful. We now have our most important functionality working. My only complaint is that the image is kind of blurry, so I'm going to implement this other idea I have. I think it will be best just to show it. Here's the new function with the color image. That looks way better. And now with a cat. The next thing for us to do is represent the internet. Up until now, all of these transmissions have happened in a local network. Let's start by expanding that local network and adding a more robust address system. Now each computer has two addresses. You can think of them like internet and local addresses. Target addresses will now always be the IP address, and if the IP is part of the local network, the computer will send the information with the target computer's local address attached. If it's outside of the local network, then the local address will be set to this router's local address, and from there it will be forwarded to the internet router. This is the breakdown of the full process of a ping going outside of the local network. The computer recognizes the target IP is out of the local network and sets the destination to the local router via the switch. The local router sends the data to the internet router with a direct link. The internet router replaces the MAC address with a new one and sends it to the other local router based on its routing info. The new local router finds the matching IP within the local network and sends it to that computer via the switch. And then the same process basically happens in reverse because the computer that received the message now has the IP of the computer that sent it in the first place. There we go, we have the internet. All it's missing is an ISP, firewall, servers, ports, data centers, and a bunch of other stuff. And a number of these systems have been simplified to give a general overview of what's happening when we send information across the internet. I haven't posted the build of this project because there's not much to it apart from what's been shown here, but for the next project, I should have something that's shareable. Thanks for watching the video and for everyone's support. Until next time.